Okay, this is our first podcast of Unit 7, where we're going to be talking about chemical reactions, and we're going to start off by balancing chemical reactions. This might sound familiar. You should have done this in middle school at some point, maybe just a little bit, but we're going to go a little farther with it today. So, in our packet, you're going to be doing pages 2 and 3, and I'm going to do most of it with you, but those last two problems are going to be on your own, and you're not going to get a stamp on your podcast unless you finish those out. So, let's look at this. First, what is a chemical equation? Well, technically, it's a symbolic representation of a chemical reaction, where we use symbols, the symbols from the periodic table, to tell us what chemicals are reacting. So, that's really a pretty basic explanation. What we really need to know about the basics of a reaction is that in a reaction, the stuff before the arrow, what we call the reactants, that's the stuff that reacts, and it produces the products. So the reactants is the left side of the arrow, products are the right side of the arrow. And like I just said, that arrow kind of means something. That's where the reaction is happening. There's some other symbols that we'll see in these reactions too. That arrow is always going to be in every single reaction. And that's where something reacts, or it produces that stuff after the arrow. Now, sometimes you might see something written on top of the arrow. Like here it says MnO2 or anything. That's a chemical. Sometimes it's a catalyst or something. It's not actually part of the reactants or the products. It's not part of the reaction itself, but it's helping kind of push it along. It's doing something to help the reaction. So that's still the arrow, so that's still reacting, but it's reacting in the presence of that chemical. You don't really care what that chemical is unless it's down on the reactant or product side. Similarly, you might see a little triangle or the word heat or energy or electricity written someplace in a reaction, and sometimes that's going to be on top of the arrow, just like those chemicals will. But that's another thing. Some reactions need heat or energy in order to move forward, so it has to be part of the reaction, but it's not really a chemical. It's just another thing that's involved in the reaction. Now, these other things in the parentheses are states of matter. S, L, and G are solids, liquids, and gases. Pretty straightforward. We've seen AQ before. That means aqueous, means that thing is dissolved in water. So it kind of acts like a liquid because it's in the water, but it's not technically a liquid, because to be a liquid, that substance would have had to be melted. So aqueous solutions let us have a reaction that mixes well because of those liquid kind of properties, but it's not actually it doesn't have to be at as high of a temperature to actually get it to melt. But we don't really need those in our reactions right now, but they will give us some more information about our reactions later on. So we'll come back to those later. A chemical reaction in general will tell us three things about that reaction: the amount of reactants and products, the ratio of those reactants and products, and then the third, that tells us if a reaction is reversible. So we're not going to spend a whole lot of time talking about reversible reactions, but some people don't realize that a chemical reaction, a chemical change, can be reversed. And if it can, then you're not just going to see a normal arrow, you're going to see a double-sided arrow in that reaction, showing you that it can go either direction. So those are really the three general things a reaction tells us. And then we are going to need these diatomics. We've talked about them before, but these diatomics are elements that can never be by themselves. They have to have a buddy. So in a compound like sodium bromide, NaBr, bromine has a buddy. But if you just have a chunk of bromine, the Brs can't be by themselves. So what happens there is that the Br is going to get a 2 on it. So these are the 7 elements that can never be by themselves: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. There's a couple other ways to remember them, and I can remind you those in class or in the next podcast. But these are important for when we're writing out our reactions. Remember our diatomics. So let's actually get into this balancing stuff. So balancing is all about getting the same number of atoms of each element the same on each side of the reaction, because we can't have any magic happening in chemistry. There's no magically appearing elements or atoms. If they weren't there before the reaction, we can't have them just magically pop up after the reaction. And kind of the opposite is true too. I can't have any atoms before the reaction in the reactants that just disappear and aren't in the products. Everything I start with in a chemical reaction is still there at the end It's just been rearranged. So sometimes the reactions don't look like they're balanced, or they don't look normal. They look like there's some magic happening. And so what we're going to do is balance those reactions in order to prove and kind of show that there's no magic happening, kind of track where everything's moving and going to. So the first step in balancing a reaction is actually to get the reaction itself. It says here, step 1 and 2 is to determine the correct formula for all the reactants and products and put plus signs and arrows in between them. But really, we're going to leave this till later. We're going to start by just balancing, because there are going to be times where you have to write out the reaction and balance it, but we'll get to that later. So the balancing part really technically starts at step 3. We're going to start by counting the number of atoms of each element. And sometimes we're not going to pay attention to individual elements. If we have a polyatomic, something like nitrate, that's NO3, we're going to keep that as a group and count how many nitrates we have before and after the reaction, instead of how many N's and O's. It makes it a little bit simpler for us. So we're going to count how many of each thing we have on each side of the reaction, each side of that arrow, and try and make it the same. If it's already the same, you don't have to do anything. But if it's different, then we're going to have to put coefficients. Each of those elements, we're going to look at them one at a time, put coefficients in front of one of those substances in order to try and make them balanced. We're not going to change the formulas themselves, we're just going to change how many of them we have. Now, when we do this, it's not really a set order. You're just going to basically look at the elements in your equation and look at each of them one by one. I usually just go left to right and balance each of them individually. But sometimes it's a little bit helpful if you leave hydrogen and oxygen till last. And I would definitely say leave oxygen until last. It gets complicated and into everything. It's weird and crazy, and yeah. So my rule, and it's probably a rule that you've heard before, and it's not really a chemistry rule, but I'm making it a rule, is take care of your bros first. Everything on the periodic table is your bro, except for those H's and O's. As we take care of our bros first, and then our H's and O's can go last, because they get into everything and make a big trouble and make everything harder to balance. So I'm not going to say that rule out loud, but you might have just kind of remembered that rule to yourself. Bros first, and then take care of your H's and O's last. So general rule might help, but if you do them in a different order, it just might mean that you have to go back and fix some things over and over again. So it's not the end of the world if you forget. So you're going to count an element, change a coefficient to get it balanced. Look at another element, change something if you have to. And you're just going to keep going back and forth, changing coefficients until every element has the same number of atoms on each side. Now, once you're sure everything is equal on both sides, you still might have a little bit of work to do, because this reaction, those coefficients, always have to be reduced in their lowest possible ratio. And sometimes you might just kind of keep going a little bit too far, and they might end up getting too big. Like this reaction. If I have 2, 2, 2, 2 as my coefficients all the way across, technically we could divide all of those by 2, and that turns into 1, 1, 1, 1. So once you're done, double check your coefficients and make sure that they can't be reduced, because it is not actually 100% correct unless it's in its fully reduced form. Similarly, it doesn't all have to be the same number. If it's 4, 2, 4, 2, these all can still get divided by 2, and that would reduce down to 2, 1, 2, 1. So that's our process. So let's actually get going with this. Do some examples. So in this first example on page 2, I'm looking at this, and I'm just going to go from left to right. I have one Na here, one Na over here. Our dividing line is that arrow. So I'm looking on both sides of that arrow. 1 Na means that's balanced. I'm not going to do anything. Then I'm going to go on to my next element, which is Cl, chlorine. And over here I have 2 chlorines, but over here I just have 1. So I'm going to have to fix that. And I can't get rid of this 2. All that I can do in order to balance is change the number, add a coefficient up in front of that substance. And so instead of making this Cl have less, this side have less chlorines, then what I'm going to do is make this side have more until I can get to 2 chlorines. So I'm going to put a number here, and this number is going to multiply by how many chlorines I already have, and I want 2 when I'm done, so that number that I'm going to put up front is a 2. So 2 times 1 is 2, now I have 2 chlorines. Now unfortunately I kind of messed up my sodiums, because even though before they were nice and neat, this 2 applies to everything in this compound. It doesn't skip over the Na on the way to the Cl. So now I have 2 Nas on this side as well, but I can't help it. That 2 has to be there to fix the Cls. So what I have to do is come back over to this side and fix those Nas. So now I have 2 sodiums on each side and 2 chlorines, and this equation is balanced. Now you could just stop here. I like to fill in with 1s though, so that I know that I'm done and I didn't just kind of stop halfway through and get distracted and forget to come back to it. I like to fill in all my blanks, but you never have to fill in that 1, because it's understood. If I wrote the Cl2 there, I have at least one of those sitting there. So that's our reaction, done and balanced. In our second example, I have 1 zinc on each side, so that's good. 1 H here, 2 H's here. So I'm going to go ahead and fix that up by putting a 2 here. Now, as I move on, that also means I have 2 Cl's, but I wanted 2 Cl's because this side has 2 already. So this is balanced with just that 1 number there, but I'm going to go ahead and fill in my 1s to show that I'm done. In our third example, it's a little bit longer, but I still take it 1 element at a time. Got 1 K here, 1 K there, okay. Br is 1 on this side, 2 on this side. So I am going to have to fix that up by putting a 2 here, but that also kind of messed up those K's that I just had. There's 2 K's now, so I'm going to come over here, I don't like that 2, and put a 2 here so that I get 2 K's there. And keeping going, my K's and my BR's are good. 1 Mg, 1 Mg, 2 Cl's. And this 2 also means I have 2 Cl's there. So this is now balanced, 2, 1, 2, 1. In our next example, we've got this parentheses here. So my calciums are good to start with. So really I'm just going to jump into these oxygens. This oxygen, it just looks like there's 1, but because it's in this parentheses, and the parentheses has this 2 on the outside, that applies to everything in here. So I technically have 2 O's and 2 H's there. This also gets a little complicated because I've got H's in 2 places over here as well. There's 2 here and 1 here. So that can happen. And remember, what we're doing is balancing before and after the arrow. So sometimes it helps people to put a line at that arrow to remind themselves, if I do have the same element on the same side in 2 different compounds or 2 different places, we do have to add those together because it's the total number of hydrogens before the arrow that has to be equal to the total number of hydrogens after the arrow. It's not just the total hydrogens in each compound. So let me clean this up just a little bit. We've talked about it, but I don't really like it getting messy. But if you want to show your work that helps you not make mistakes, some of those markings might help you like remember to link these 2 together and add those H's up. So calciums were good. Got 2 O's over here, like I said. So now let's put a 2 here so that I can get 2 O's. Then I've got 2 H's plus 1 H is 3 H's. And over here I have 4 H's. So I need to get some more H's on that left side, the reactant side. And in order to do that, in order to get 4, I'm going to leave these 2 H's alone. And I'm just going to put a 2 up front here so that I got 2 here and 2 here gives me the 4 that I need. Now that 2 also applies to the H and the I, and so I've got 2 I's on the reactant side and 2 I's on the product side. So this is balanced. 1, 2, 1, 2. We got this last example here before we move on to the next page. And it's pretty straightforward, pretty simple, hopefully, like one of those first ones. So I'm actually not going to balance this one for you. I think if you look at this, you can get it pretty easily and get that balanced. Check with me tomorrow if you need to make sure you got that. But let's move on to the next page, where we're actually going to start writing out word equations as normal equations with the symbols to represent them. And then, yes, we're still going to have to balance them. But we've already learned how to write out chemical equations and formulas for chemicals, and that's all that this is turning the words into formulas. So, zinc, Zn, element. When we have an element, we need to check those diatomics that we talked about at the beginning of this podcast, because there are 7 elements that can never exist by themselves, those Brinkelhoff elements. But luckily for us right now, Zn is not one of those, so it's just plain old Zn. Then it says plus hydrochloric acid, so we're going to add hydrochloric acid, it's HCl. We can talk a lot more about acids, and I can repost that podcast that goes over them so that you can get a little bit more help. But basically, hydro means there's no O's. Every acid starts with H, and because there's no O's, that's just H. And then chloric tells me that that's chlorine with it. And that's when I just check charges. +1, -1, shove them together. So, like I said, don't worry about acids too much. There's not going to be any acids on your quiz, that first quiz of the unit. So what I really want you to focus on is the rest of these compounds and elements. Focus on the reaction part, not the acid part. And this one shows me I need to put my arrow there. And then zinc chloride is going to be Zn and Cl together. But when I have a compound like this, if it doesn't have prefixes in it to tell me like zinc dichloride or like tri-zinc dichloride, if it doesn't have prefixes telling me how many of each element I need to check the charges to figure that out. So zinc, Zn, has a +2 charge. It's one of those transition metals that has a set charge. And then chlorine has a -1. Because these do not automatically cancel each other out, we have to cross-drop reduce. So the 1 is going to be coming over onto the zinc, and that 2 comes over onto the chlorine. And we're crossing over. We're going to drop those signs, no more plus and minus. And then that reducing step is like when we reduced our equation. If there is a common denominator, we'll divide by it. But there's not here, so all that turns into is that 2 come into the end. We don't have to write the 1. And it says plus hydrogen. Hey, that's easy. Hydrogen is H. But remember, when we have a lonely little element, we have to check diatomics. And hydrogen is a diatomic. But all that means is I add a 2. Notice there is not a 2 in the formula over here. Don't expect equations to automatically be balanced. That's kind of weird if they start off balanced like they're supposed to be. So don't expect it to be balanced when you're writing out these reactions. We're still going to have to balance them after we write it out. And even though hydrogen is a diatomic, over here, hydrogen's not diane. It's not on its own. It's got a buddy in that chlorine. It's only when it's an element form of that specific diatomic that it has to get that 2 on it. So this is our reaction written out. And now to balance it, let me change colors real quick. I've got 1 zinc on each side, 1 H on this side, so let's put a 2 there. Gives me 2 H's and 2 Cl's, which is all that I needed. So 1, 2, 1, 1 is our reaction. In our second word equation, it says aluminum carbide. So I've got aluminum and carbon. And checking charges, aluminum has a +3, carbide has a plus or -4, but in this case, it's going to have to be -4. We really don't care about those signs, though, because we're about to cross-drop and reduce those out anyway. So they don't cancel, so we're going to switch them. Turns into Al4C3. And I say that this reacts with, so that's our plus sign, water. We need to know water is H2O. To form is our arrow. Methane, it tells us, is CH4. And then aluminum hydroxide, okay? So and is the plus sign. And then aluminum is Al, like we saw before. Hydroxide isn't just hydrogen. It isn't just oxygen. It's both of them. This is one of those polyatomics on the back of the periodic table. But just like any other compound, when we've got more than one element together, no prefixes in there, we have to check charges. So aluminum is a +3, just like it was before. Hydroxide is a -1, according to that polyatomic chart. So they don't cancel. We have to cross, drop, reduce. And when we cross that 3 over onto the hydroxide, we have to remember to put it in parentheses. So that is our word equation here. Going through, just going to balance this real quick and get our ALs balanced and our Cs balanced. And now our H's are going to be kind of a pain. So I've got 3 times 4 is 12 H's here. And then this is another 12 H's here. So that's 24. So to get 24 H's on this side, I've got to put a 12. Then that means I have 12 oxygens, too. But that actually makes sense because there's a 3 here for 3 oxygens times the 4 up front means I've got 12 oxygens. So 1, 12, 3, 4. Wow, that's kind of a big one. But that's what it's got to be. Can't reduce it. And I think this is going to be the last one. Actually, we might have one more after this. But, oh no, we have a couple after this. Well, let's go through these pretty quick. It's got potassium bromide, so I've got KBr, and checking charges, that's a +1 and a -1, and it says is mixed with a solution of barium acetate, okay? So I know barium, and acetate is that big crazy group on the back. If I check charges, barium is actually a +2, and acetate is a -1, so cross, drop, reduce, turns into, put that acetate in parentheses with a 2 on the outside. And then this forms potassium acetate. So now potassium's with that acetate. Although, like we saw before, potassium has that +1 charge. Acetate is -1. It's the same piece as we saw before, so we kind of should remember those charges. So those just get to stay together. And barium bromide. So Ba and Br get together. Barium still has that +2, and bromine has a -1, so that becomes BaBr2. Balancing this out, and if you notice that acetate is the first thing that I saw, that I had 2 of them here, and just 1 of them here. So I'm going to go ahead and put a 2 here. That also gets me 2 Ks, so I'm going to put a 2 here. That also gets me 2 Brs, and hey, that's what I wanted, 2 Brs. So everything else is balanced now. 1, 2, 1, 2, 1. And at least this one's nice and short. This says copper, so I know copper is Cu, but remember, even with a simple little element like copper, we have to check our diatomics. So luckily Cu is not in that Brinkelhoff, so it's just Cu. Reacts with oxygen, that is a diatomic, to produce copper 2 oxide. So this does have copper and oxygen together. And let me talk about that Roman numeral real quick, because Cu and O are getting together. If we try and check the charges on here, we know oxide has a -2 charge, because it's the whole column does on the periodic table. But copper is a transition metal, and we don't know what its charge is. But that's why there's the Roman numeral here. It's trying to help you get that charge. So this is copper +2 with oxygen -2. So those just cancel out. I don't actually have to add anything to that formula. Don't let those Roman numerals scare you. At the very least, just write 1 of each. Sometimes that ends up being the right answer. Now, this isn't balanced, but we can do that pretty quick and easy. There's 2 O's, that gets me 2 O's, and then 2 Cu's. So 2, 1, 2, nice short reaction. And now this is the last one that we're doing together. Tetraphosphorus decoxide. Might seem like a big crazy name, but it's trying to help you. This has prefixes in it, so we don't have to cross, drop, reduce. We don't have to check charges or any of that. Tetra means 4. So I have 4 phosphorus, dec means 10, so there's 10 oxygens, so P4O10 is my formula. It says, and water react to form phosphoric acid. So honestly, this one wasn't that hard to write out. And balancing it, I've got this 2 and this 3 with the H's, but I'm not going to worry about that quite yet, actually. Let's P's first. 4 P's here. I put a 4 here to get 4 P's. And now H's, then O's. As remember, bros first. I took care of P, and then H's, then O's. Bros, then H's, then O's. So H's here, I have 2 H's. Over here I have 12 H's. So let's go ahead and put a 6 here. And then O's, I have 16 O's here. And on this side I have 2 different O's. I have 10 here and 6 here. Oh, that's 16. So because I took care of my H's first, my O's just worked themselves out. That was awfully nice of them. So 1, 6, 4. So I know this was a bit long, but I wanted to go through more of these examples with you than kind of just doing 1 or 2, because we need some help and some reminding of how to write formulas, I think. So you have 2 examples to do on your own. Notice that this one has iron 3 oxide, and the next one, it's a lot like that copper 2 oxide. So go back and look at that example and how we worked that one out if you're stuck on that. But you have to do these if you want to get your stamp on this page. So good luck. Come in and ask me ahead of class if you need help with them, and I'll help you get those done. But that's it for this podcast. Sorry it's so long.